Hello there, and welcome to the Sleepy Science channel. I'm so glad you found your way here tonight. Maybe you've had a long day filled with questions, or perhaps you're the kind of person who likes to drift off to sleep while pondering the building blocks of everything around us. Either way, you're in exactly the right place. Tonight, we're going on a journey through time, through smoke-filled laboratories and candlelit chambers, through moments of brilliant insight and centuries of patient observation. We're exploring the history of chemistry, the science that helped us understand what the world is actually made of. Before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps other sleepy souls find their way here too, one peaceful night at a time. You have nothing to do but rest. Let your breathing slow, your muscles relax, and your mind gently wander through the story we're about to tell. Because chemistry isn't just about test tubes and formulas. It's the story of humanity's long, patient effort to understand the very fabric of reality. From ancient fires to artificial atoms, from mysterious transformations to elegant equations, this is how we learned what everything is made of. Now, let's begin. The ancient foundations. Long before anyone spoke the word chemistry, humans were already chemists. They just didn't know it yet. Somewhere in the deep mists of prehistory, perhaps around 1 million years ago, our ancestors learned to control fire. This was humanity's first chemical reaction, harnessed and directed. When wood burns, it transforms. Solid matter becomes heat, light, smoke, and ash. Something fundamental changes. The wood doesn't simply disappear. It becomes something else entirely. This transformation, this change of one substance into another, is the very heart of chemistry. But fire was just the beginning. By around 10,000 years ago, as the last ice age released its grip on the world, humans were fermenting grain and fruit to make beer and wine. They didn't understand the invisible microorganisms working their magic, converting sugars into alcohol through a process we now call fermentation. They simply knew that if you prepared certain materials in certain ways and waited, something wonderful happened. The liquid changed. It gained new properties. It could alter consciousness, preserve nutrients, and bring a people together in celebration. This, too, was chemistry, happening in clay vessels and wooden barrels, transforming the everyday into something special. Around 5,000 years ago, in the river valleys of Mesopotamia and Egypt, people began extracting metals from rocks. Copper could be pulled from greenish stones through a process called smelting. You heated the ore with charcoal in a furnace hot enough to melt the metal. The copper would pool at the bottom, liquid and gleaming, separated from the dross and slag. This wasn't magic, though it must have seemed close. This was chemistry. The ore wasn't simply hiding the metal. The heat was actually changing the chemical bonds, releasing the copper from the oxygen and sulfur it was bound to. Then came bronze, and everything changed. Someone, somewhere, discovered that mixing copper with tin created something better than either metal alone. Bronze was harder, more durable, able to hold a sharper edge. This discovery was so significant that we named an entire age of human history after it. The Bronze Age, beginning around 3,500 years before the Common Era, represents humanity's first deliberate creation of an alloy, a substance that didn't exist in nature. This was chemistry as technology, chemistry as power. The ancient Egyptians were master chemists in their own right, even if they wouldn't have called themselves that. They developed complex processes for making glass, creating pigments that would last thousands of years, and preserving the dead through mummification. The process of mummification alone involved a sophisticated understanding of how different substances interacted with organic tissue. They used natron, a naturally occurring mixture of sodium salts, to dry the body. They employed various resins and oils, each chosen for specific properties. They understood, at least practically, that certain substances could prevent decay, could preserve what would otherwise crumble to dust. In ancient China, similar developments unfolded. Chinese artisans discovered how to make porcelain, a ceramic so refined and elegant that Europeans would spend centuries trying to replicate it. They developed gunpowder, a mixture that would eventually change warfare forever. They extracted medicines from plants, developing pharmacopoeias that cataloged hundreds of natural substances and their effects on the human body. But it wasn't enough to simply know how to do things. The human mind craves understanding. It wants to know not just what happens, but why. The ancient Greeks, particularly from around 600 years before the Common Era onwards, began developing theories about the nature of matter itself. Thales of Miletus proposed that water was the fundamental substance from which everything else derived. Heraclitus argued for fire. Empedocles synthesized these ideas, suggesting that everything was made of four elements: earth, water, air, and fire. Later, Aristotle added a fifth element, the quintessence or ether, which he believed filled the heavens. These ideas might seem quaint to us now, but they represented something revolutionary. They were attempts to explain the diversity of the world through simple underlying principles. If everything was made of combinations of these basic elements, then perhaps you could transform one substance into another by changing the proportions of elements within it. This idea, this notion that transformation was possible, that lead might become gold if only you understood how to rearrange its fundamental nature, would echo through the centuries. It would inspire thousands of years of investigation, frustration, discovery, and eventually, genuine understanding. The Greek philosopher Democritus, working around 400 years before the Common Era, proposed something even more radical. He suggested that if you kept dividing matter into smaller and smaller pieces, you would eventually reach a point where you couldn't divide it anymore. These ultimate particles he called atomos, meaning indivisible. Here was the seed of atomic theory, planted more than 2,000 years before anyone could prove atoms existed. Most ancient thinkers rejected Democritus's ideas. Aristotle's influence was stronger, and his theory of continuous matter, infinitely divisible, held sway for centuries. Meanwhile, practical chemistry continued to advance. Roman engineers developed hydraulic cement that could set underwater. Chinese metallurgists were producing high-quality steel. Indian chemists were extracting and purifying various substances. developing techniques that would later spread along trade routes. The ancient world had accumulated an impressive body of chemical knowledge, even if the theoretical framework to explain it all remained elusive. They knew how to transform materials, how to extract and purify substances, how to create new compounds. What they lacked was a systematic way of understanding why these transformations worked. The stage was set for the next great chapter in chemistry's story, one that would blend mysticism and methodology, symbolism and experimentation, in a tradition that would last more than 1,000 years. The Age of Alchemy. As the ancient world transitioned into the medieval, a new tradition emerged that would dominate chemical thought for over a millennium. This was alchemy, a practice that combined practical experimentation with philosophical speculation and spiritual seeking. Alchemy was born from the meeting of Greek theory, Egyptian craft traditions, and various mystical philosophies. It was never just one thing. It was simultaneously a practical art, a philosophical system, and, for many practitioners, a spiritual path. The word alchemy itself tells a story. It comes from the Arabic alchemia, which in turn derives from the Greek chemeia. Some scholars believe this Greek word came from chem, the ancient Egyptian word for their land, referring to the black, fertile soil of the Nile Delta. Others trace it to kaimaya, meaning the art of alloying metals. Either way, the word carried connotations of transformation, of taking base materials and creating something precious. The earliest alchemical texts we have come from Hellenistic Egypt, particularly from Alexandria, that great cosmopolitan city where Greek, Egyptian, and Jewish learning mingled. Zosimos of Panopolis, writing around 300 years after the Common Era, produced some of the first systematic alchemical treatises. His works described laboratory equipment, chemical processes, and allegorical visions in equal measure. For Zosimos and alchemists who followed, the work in the laboratory was inseparable from inner spiritual development. The transformation of lead into gold was both a literal goal and a metaphor for the purification of the human soul. When the Roman Empire fell, and Europe descended into what we call the Dark Ages, alchemical knowledge found new champions in the Islamic world. The Islamic Golden Age, roughly from the 8th to the 13th centuries, saw extraordinary advances in many fields, and alchemy was no exception. Muslim scholars translated Greek texts, studied them, expanded upon them, and conducted their own experiments. They were systematic and rigorous in ways that would lay foundations for experimental science. Perhaps the most famous Islamic alchemist was Jabir ibn Hayyan, known in the Latin West as Geber. Working in the 8th and 9th centuries, Jabir wrote extensively on chemical processes. He described how to prepare various acids, including sulfuric acid and nitric acid, substances that would become fundamental tools of chemistry. He systematized alchemical procedures, describing operations like calcination, where substances are heated to powder, sublimation, where solids are turned to vapor and back, and distillation, where liquids are separated by their different boiling points. These weren't mystical operations. They were practical techniques that actually worked, techniques still used in modified form today. Jabir also developed theoretical frameworks. He proposed that metals were composed of different proportions of sulfur and mercury, not the elements we know by those names today, but philosophical principles representing combustibility and liquidity. If you could adjust these proportions just right, he theorized, you could transform one metal into another. This theory was wrong, but it was sophisticated, attempting to explain observations through underlying principles. The Islamic alchemists pursued three great goals. The first was chrysopoeia, the transmutation of base metals into gold. The second was the creation of an elixir of life, a substance that could cure all diseases and extend life indefinitely. The third was the formulation of a universal solvent, something that could dissolve anything. These goals were ambitious, perhaps impossible, but the pursuit of them led to genuine discoveries. In seeking to transform lead into gold, alchemists learned how to purify metals, to identify substances, to control chemical reactions with precision. When alchemical knowledge returned to Europe in the 12th and 13th centuries, translated from Arabic into Latin, it sparked an explosion of interest. European scholars and practitioners embraced alchemy with enthusiasm. The translation movement brought not just alchemical texts, but also works of Greek philosophy, mathematics, and natural science that had been preserved and expanded in the Islamic world. Medieval Europe suddenly had access to a wealth of learning. European alchemy took on its own character. It became deeply intertwined with Christianity. The transformation of base metals into gold was seen as analogous to the resurrection of Christ, turning death into life. The philosopher's stone, that legendary substance that could enable transmutation, was sometimes compared to Christ himself, the spiritual catalyst that transforms humanity. This religious dimension gave alchemy a kind of spiritual legitimacy, but also made it potentially dangerous. The Church was suspicious of practices that seemed to promise godlike powers of transformation. Albertus Magnus, a German Dominican friar of the 13th century, wrote extensively about alchemy. He approached it as a natural philosopher, attempting to understand it through Aristotelian principles. He was skeptical about some alchemical claims, but believed that the transmutation of metals was theoretically possible if one could truly understand and manipulate the fundamental qualities of matter. His student, Thomas Aquinas, also engaged with alchemical ideas, though many alchemical texts later attributed to him were likely forgeries, a common practice that gave texts added authority. Roger Bacon, an English Franciscan friar of the same era, was another important figure. He emphasized the importance of experimental verification, arguing that knowledge should come from experience and observation rather than just from ancient authorities. This was a radical position for the time, when scholarship often meant poring over old texts. Bacon's emphasis on experiment and mathematics helped pave the way for the scientific method that would eventually emerge. The philosopher's stone became the central obsession of European alchemy. This legendary substance, sometimes described as a red powder, sometimes as a dense stone, was said to be capable of transmuting any amount of base metal into gold. A tiny grain of the stone, dissolved in liquid, could transform an entire crucible of lead into pure gold. Beyond this, the stone could create the elixir of life, a potion granting health, youth, and perhaps immortality. Medieval and Renaissance texts described elaborate procedures for creating the stone, often written in symbolic language to hide the knowledge from the unworthy. The recipe might call for the green lion devouring the sun, for the philosophical Mercury, for the marriage of the red king and white queen. These weren't literal instructions but coded language, allegories layered upon allegories. Did anyone ever succeed? Tales circulated of successful transmutations. Nicolas Flamel, a 14th century Parisian scribe and manuscript seller, was said to have discovered the secret and created gold, which he then used for charitable works. The story is almost certainly legendary, but it persisted for centuries, inspiring seekers. Many alchemists claimed success, but examined carefully, their claims always fell apart. The gold they produced had usually been hidden beforehand, concealed in equipment or materials. The whole demonstration was an elaborate fraud, sometimes to attract wealthy patrons, sometimes to fulfill their own desperate need to believe. But not all alchemists were frauds or fools. Many were sincere seekers, brilliant experimentalists who genuinely advanced chemical knowledge even as they pursued impossible goals. They developed equipment that would become standard in later chemistry: alembics for distillation, furnaces for heating substances to high temperatures, methods for crystallization and precipitation. They learned to identify substances by their properties, to keep careful records of experiments, to vary procedures systematically to see what changed. Alchemy also developed an elaborate symbolic language, a visual vocabulary of dragons and serpents, suns and moons, kings and queens. These symbols had multiple meanings, sometimes representing actual chemicals, sometimes stages in a process, sometimes spiritual states. This symbolic richness gave alchemy a cultural power beyond its practical results. It appeared in art, literature, and religious thought. It captured the imagination in a way that dry natural philosophy never could. By the 16th century, alchemy was reaching its peak in Europe, but also beginning to transform. Paracelsus, a Swiss physician and alchemist born in 1493, argued that alchemy's real purpose wasn't making gold but making medicines. He believed that diseases were caused by imbalances of chemical substances in the body, and that chemical remedies could restore balance. This iatrochemistry, or medical chemistry, shifted the focus from metallic transmutation to pharmaceutical preparation. Paracelsus was abrasive, controversial, and revolutionary. He rejected much of the medical wisdom of his time, burned classical texts, and insisted that experience and observation mattered more than ancient authority. His approach was part of a broader shift toward what we might recognize as science. Through all these centuries, from ancient Alexandria to Renaissance Europe, alchemy had accumulated an enormous body of practical chemical knowledge. Alchemists knew how to work with acids and alkalis, how to precipitate metals from solutions, how to purify substances through repeated distillation. They had developed theories about matter, admittedly theories that were wrong, but theories that could be tested and refined. They had created a tradition of experimental investigation, of manipulating matter to learn its secrets. What they hadn't done was establish clear criteria for what counted as knowledge, for how to separate real discoveries from wishful thinking. That transformation was about to begin. The birth of modern chemistry. The 17th century brought changes that would transform alchemy into chemistry, mysticism into science. This wasn't a sudden revolution. It was a gradual shift in how people thought about matter and how they investigated it. The key was separating what could be verified through careful experiment from what rested on speculation, symbolism, or fraud. Robert Boyle stands as a pivotal figure in this transformation. Born in 1627 in Ireland, Boyle came from wealth and could dedicate his life to natural philosophy. He was deeply influenced by the new mechanical philosophy emerging in his time, which suggested that the universe operated like a vast machine, following natural laws that could be discovered through observation and reason. In 1661, Boyle published The Skeptical Chemist, a book that challenged the foundations of alchemical thought. Boyle questioned the Aristotelian theory of 4 elements. He argued that elements should be defined not by philosophical tradition, but by experimental evidence. An element, Boyle suggested, should be a substance that couldn't be broken down into simpler substances by chemical means. This was a radical, empirical definition, one that would eventually lead to our modern understanding of elements. Boyle also rejected the alchemical mercury-sulfur theory of metals. He insisted that chemistry needed to move beyond symbolic language and vague analogies toward precise, repeatable experiments that could be independently verified. Boyle was also a brilliant experimentalist. Working with his assistant Robert Hooke, he improved the air pump and conducted experiments on the properties of air and gases. In 1662, he published Boyle's Law, describing the relationship between the pressure and volume of a gas. When temperature is constant, pressure and volume are inversely proportional. If you compress a gas into half its original volume, its pressure doubles. This was a mathematical relationship, precise and measurable, very different from the qualitative descriptions common in earlier chemical thought. Despite Boyle's skepticism of traditional alchemy, he never entirely abandoned hope for transmutation. He spent years conducting experiments trying to transform metals, though without success. This shows how gradual the transition was. Even someone as empirically rigorous as Boyle couldn't completely let go of alchemical dreams. But his emphasis on careful experiment, precise measurement, and skepticism of untested claims pointed chemistry in a new direction. The late 17th and early 18th centuries saw an explosion of investigation into gases. Before this, air had been considered a single element, one of Aristotle's 4. Now, chemists began to realize that air was actually a mixture of different gases, each with distinct properties. In 1774, Joseph Priestley, an English minister and natural philosopher, isolated a gas by heating mercuric oxide. Mice placed in jars of this gas lived longer than in ordinary air. Candles burned more brightly. Priestley had discovered oxygen, though he called it dephlogisticated air, a name that made sense within the chemical theory of his time. That theory was called phlogiston theory, and understanding it helps us appreciate how science progresses. According to this theory, developed by German physician Georg Ernst Stahl In the early 1700s, combustible materials contained a substance called phlogiston. When something burned, it released its phlogiston into the air. The ash or residue left behind was the material without its phlogiston. This theory explained many observations. Wood burned and turned to ash because it released phlogiston. Metals heated in air became calyxes, crumbly oxides, because they lost phlogiston. Air became saturated with phlogiston, which is why fires eventually went out in closed containers. Phlogiston theory was wrong, but it was a genuine scientific theory. It made predictions that could be tested. It unified various phenomena under a single explanatory framework. It worked well enough that some of the best chemists of the 18th century believed in it. But it had problems. When metals burned, forming oxides, they gained weight rather than losing it. If burning released phlogiston, why did things get heavier? Phlogiston theorists propose that phlogiston might have negative weight, or that it was somehow associated with the air around the burning substance. These were increasingly awkward explanations, patches on a theory that was fundamentally flawed. The person who finally overthrew phlogiston theory was Antoine Laurent Lavoisier, a French chemist born in 1743. Lavoisier brought to chemistry a new level of quantitative precision. He conducted experiments where he carefully weighed everything: the reactants before a reaction, the products after, any gases evolved or absorbed. He demonstrated the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed, only transformed. The total mass of all reactants equals the total mass of all products. In 1777, Lavoisier published results showing that when substances burned, they combined with a portion of the air. He named this active portion oxygen, from Greek words meaning acid former, because he believed all acids contained oxygen. This wasn't entirely correct, but it was much closer to the truth than phlogiston theory. Lavoisier showed that combustion wasn't about releasing phlogiston, but about combining with oxygen. Rusting of metals was the same process happening slowly. Breathing involved animals consuming oxygen and producing carbon dioxide. Lavoisier revolutionized chemistry in other ways too. In 1787, he worked with colleagues to develop a new system of chemical nomenclature, a standardized way of naming substances based on their composition. Instead of colorful alchemical names like butter of antimony or flowers of zinc, chemicals would have systematic names that indicated what elements they contained: sulfuric acid, hydrochloric acid, sodium chloride. This might seem like mere bookkeeping, but clear, consistent naming was essential for chemistry to advance as a science. It allowed chemists to communicate precisely about substances and reactions. In 1789, Lavoisier published his Elementary Treatise on Chemistry, the first modern chemistry textbook. It presented chemistry as a rational science based on experiment and measurement. It included a list of elements, substances that couldn't be chemically decomposed into simpler substances. Lavoisier's list included some genuine elements like oxygen, nitrogen, sulfur, phosphorus, and various metals. It also included light and heat, which we now know aren't material substances, and it didn't include elements that hadn't yet been isolated, like sodium and potassium. But it was a start, a foundation that could be built upon. Lavoisier's life ended tragically. During the French Revolution, he was arrested partly because of his work as a tax collector for the old regime. Despite his scientific stature, he was guillotined in 1794. It's said that the mathematician Joseph Louis Lagrange commented, "It took them only an instant to cut off his head, but France may not produce another like it in a century." Lavoisier was gone, but his chemical revolution continued. Other chemists were also discovering new gases and understanding their properties. Carl Wilhelm Scheele in Sweden had actually isolated oxygen before Priestley, though his work was published later. He also discovered chlorine, though its identity as an element wasn't immediately recognized. Henry Cavendish in England isolated hydrogen in 1766, showing that it was a distinct gas, inflammable and very light. Later experiments by Cavendish showed that when hydrogen burned in oxygen, the product was pure water. This demonstrated that water wasn't an element but a compound, made of hydrogen and oxygen. All these discoveries were breaking down the old Aristotelian four elements. Earth, water, air, and fire weren't fundamental at all. Water was a compound. Air was a mixture. Fire was a process, not a substance. Earth was countless different substances. The old framework was crumbling, and a new one, far more complex but far more accurate, was rising to take its place. By 1800, chemistry was recognizably modern in its methods and much of its understanding. But the picture was still incomplete. What was the nature of these elements? How did they combine to form compounds? Why did different elements combine in specific ratios? These questions would drive the chemistry of the 19th century. The atomic age begins. The early 19th century brought one of the most important theoretical breakthroughs in the history of chemistry, the atomic theory. This wasn't the first time someone had proposed that matter was made of tiny, indivisible particles. As we saw, the ancient Greek philosopher Democritus had suggested something similar. But earlier atomic theories had been philosophical speculation. What John Dalton proposed in 1807 was an atomic theory grounded in experimental evidence, a theory that could explain the quantitative patterns chemists were discovering in how substances combined. Dalton was a self-taught English chemist and meteorologist. He came from a Quaker family of modest means and spent much of his life teaching in Manchester. His interests ranged from color blindness, which he studied partly because he suffered from it himself, to meteorology, for which he kept meticulous weather records throughout his life. But his most important work concerned how elements combined to form compounds. Dalton noticed something that other chemists had also observed. Elements combined in definite proportions by weight. If you made water by burning hydrogen in oxygen, it always took about 8 parts by weight of oxygen for every 1 part of hydrogen. You couldn't make water with different ratios. If you used more hydrogen, some would be left over. Similarly, carbon and oxygen combined to form carbon dioxide with a fixed ratio of weights, about 3 parts carbon to 8 parts oxygen. Why should this be? Dalton realized that if matter consisted of atoms, indivisible particles, and each element had its own characteristic type of atom with a specific weight, then this pattern made perfect sense. A water molecule was formed from one atom of oxygen and two atoms of hydrogen. If oxygen atoms weighed 16 times as much as hydrogen atoms, you'd need 16 parts by weight of oxygen for every 2 parts of hydrogen, or 8 to 1. Every compound was made of molecules, specific combinations of atoms in fixed ratios. Chemical reactions rearranged atoms but didn't create or destroy them. Dalton published his atomic theory in his book, A New System of a Chemical Philosophy, released in parts between 1808 and 1827. He proposed several key ideas. All matter consists of tiny, indivisible particles called atoms. All atoms of a given element are identical, with the same weight and properties. Atoms of different elements have different weights and properties. Compounds form when atoms of different elements combine in simple, whole number ratios. In a chemical reaction, atoms are rearranged but not created or destroyed. This theory was elegant and explanatory. It accounted for the law of the conservation of mass that Lavoisier had established. It explained why elements combined in definite proportions by weight. It even explained a pattern Dalton had noticed. When two elements combined to form more than one compound, the weights of one element that combined with a fixed weight of the other were in ratios of simple whole numbers. Carbon and oxygen could form carbon monoxide or carbon dioxide. For a given amount of carbon, carbon dioxide contained exactly twice as much oxygen as carbon monoxide. If carbon monoxide had one oxygen atom per carbon, and carbon dioxide had two, this made perfect sense. Dalton also attempted to determine the relative weights of atoms of different elements. He couldn't weigh individual atoms, but he could deduce their relative weights from the proportions in which elements combined. He assigned hydrogen a weight of 1 and worked out the weights of other elements relative to that. His values weren't always accurate because he sometimes guessed wrong about how many atoms were in a molecule, but his method was sound, and subsequent chemists refined the values. Not everyone immediately accepted atomic theory. Some chemists found it too speculative, too far removed from direct observation. After all, no one could see atoms. They were theoretical entities invoked to explain patterns in measurable data. But the theory proved too useful to ignore. It provided a simple, coherent framework for understanding chemical reactions and predicting the outcomes of experiments. An Italian scientist named Amedeo Avogadro made an important contribution in 1811. He proposed that equal volumes of all gases at the same temperature and pressure contained the same number of molecules. This hypothesis, now called Avogadro's law, helped clarify the relationship between atoms and molecules, and eventually made it possible to determine how many atoms were in a molecule of a compound. Avogadro distinguished between atoms, the indivisible units of elements, and molecules, the combinations of atoms that made up compounds. Unfortunately, his ideas were largely ignored during his lifetime and only gained acceptance decades after his death. As the 19th century progressed, chemists discovered more and more elements. Some, like sodium and potassium, were isolated using the newly invented technique of electrolysis, passing electric current through molten compounds to decompose them into their constituent elements. Humphrey Davy in England used this method to isolate several elements in the early 1800s. Others were found through careful analysis of minerals and chemical compounds. By mid-century, more than 60 elements were known, and the list kept growing. Each element had distinct properties. Some were metals, shiny and good conductors of electricity. Others were nonmetals, dull and insulating. Some were gases at room temperature, others liquids, most solids. Some reacted violently with water, others not at all. Chemists cataloged these properties and looked for patterns. Were the elements completely arbitrary, or was there some underlying order? Several chemists noticed that when elements were arranged by their atomic weights, certain properties recurred at regular intervals. Elements with similar chemical behaviors appeared at regular spacings in the list. This suggested some kind of periodic law, an underlying order to the elements. Various attempts were made to organize elements into tables or charts that reflected these patterns, but the most successful and enduring was created by a Russian chemist named Dmitry Mendeleev. The periodic table and elemental discovery. In 1869, Dmitry Mendeleev, a professor of chemistry at the University of St. Petersburg, was working on a textbook. He wanted to organize the known elements in a way that would help students understand their relationships. As he struggled with this problem, he made cards for each element, writing its name, atomic weight, and properties on each card. Then, he arranged and rearranged the cards, looking for patterns. Mendeleev discovered that when elements were arranged by increasing atomic weight, their properties repeated in a periodic fashion. After a certain number of elements, you'd encounter one with properties similar to an earlier element. He arranged the elements into a table with rows and columns, placing elements with similar properties in the same column. This created a pattern, with families of elements grouped together. Alkali metals like lithium, sodium, and potassium in one column, all soft, reactive metals. Halogens like fluorine, chlorine, and bromine in another, all reactive nonmetals. Noble gases, though not all known yet, would eventually fill another column. What made Mendeleev's periodic table brilliant wasn't just the organization of known elements, it was his willingness to leave gaps. When the pattern didn't work perfectly, when an element seemed out of place or a space seemed empty, Mendeleev trusted the pattern over the immediate data. He left blank spaces in his table and boldly predicted that these represented undiscovered elements. He even predicted the properties these unknown elements should have based on their position in the table, nestled between elements with known properties. This was audacious. Mendeleev was claiming that his table could predict the existence and properties of elements never before seen. But within 15 years, 3 of his predicted elements were discovered, and their properties matched his predictions with remarkable accuracy. Gallium, discovered in 1875, fit perfectly into the space Mendeleev had left for an element he called Eka aluminum. Scandium, found in 1879, matched his Eka boron. Germanium, isolated in 1886, corresponded to his Ecce silicon. Each time, the discoverers were astounded by how closely the element's properties matched what Mendeleev had predicted years earlier. The periodic table was more than a filing system. It revealed that the elements weren't a random collection, but part of an ordered system, suggesting some deeper structure. Why should properties recur periodically? What gave each element its particular character? These questions couldn't be answered yet, but the table itself was enormously useful. It helped chemists understand relationships between elements, predict the behavior of compounds, and guide their search for new elements. As the 19th century drew to a close, the search for new elements intensified. Some discoveries came from painstaking chemical separation of rare minerals. Others came from studying new phenomena. In 1896, Henri Becquerel in France discovered that uranium compounds emitted mysterious rays that could fog photographic plates even through layers of black paper. This was radioactivity, a phenomenon that no one expected and couldn't explain. Marie Curie, a Polish physicist working in France, became fascinated by radioactivity. She and her husband Pierre worked under extraordinarily difficult conditions, processing tons of pitchblende ore to separate the radioactive elements it contained. In 1898, they announced the discovery of two new elements: polonium, named for Marie's native Poland, and radium. These elements were intensely radioactive, glowing faintly in the dark, generating heat continuously through their radioactive decay. Marie Curie's work with radioactivity would eventually earn her 2 Nobel Prizes in physics and chemistry, making her the first person to receive Nobel Prizes in 2 different sciences. Radioactivity revealed that atoms weren't truly indivisible after all. Radioactive atoms spontaneously broke down, emitting particles and transforming into atoms of different elements. This was a kind of transmutation, but not the kind alchemists had dreamed of. You couldn't control it or direct it to turn lead into gold. It happened on its own, according to the laws of physics, with each radioactive element having a characteristic half-life, the time it took for half of a sample to decay. The discovery of radioactivity and subsequent investigations into atomic structure would eventually explain why the periodic table worked. In the early 20th century, physicists discovered that atoms consisted of a small, dense nucleus containing protons and neutrons, surrounded by a cloud of electrons. The number of protons in the nucleus, called the atomic number, determined what element an atom was. Hydrogen had 1 proton, helium 2, lithium 3, and so on. The chemical properties of an element were determined by how many electrons it had, which equaled the number of protons in a neutral atom, and particularly by how those electrons were arranged. The periodic table reflected patterns in electron arrangement. Elements in the same column had similar outer electron configurations, which is why they behaved similarly in chemical reactions. The table's structure arose from quantum mechanics, the physics of the very small, which showed that electrons could only occupy certain energy levels around the nucleus. When one energy level was full, electrons had to occupy the next higher level. The filling of these electron shells created the periodic pattern Mendeleev had observed. By the early 20th century, the periodic table had been refined and expanded. New elements continued to be discovered. Some were found in nature, isolated through increasingly sophisticated chemical techniques. Others were created artificially in laboratories, synthesized by bombarding atoms with particles to produce elements that didn't exist naturally on Earth. The table that Mendeleev had constructed with fewer than 70 known elements would eventually grow to contain more than 100, each one a piece in a grand puzzle showing the ordered structure of matter, organic chemistry, and synthesis. While inorganic chemistry focused on the elements and their simple compounds, another branch of chemistry emerged in the 19th century that would transform the world in different ways. This was organic chemistry, the chemistry of carbon compounds. The name comes from an old belief that certain compounds could only be produced by living organisms, that they required some vital force present only in life. This theory, called vitalism, suggested a fundamental divide between the chemistry of life and the chemistry of inanimate matter. In 1828, a German chemist named Friedrich Wöhler made a discovery that challenged this divide. Wöhler was trying to prepare ammonium cyanate, an inorganic compound. But when he heated it, he unexpectedly obtained urea, an organic compound found in urine. He had created an organic substance from inorganic starting materials in a laboratory flask with no living organism involved. The vital force theory was called into question. Wöhler's synthesis of urea wasn't immediately seen as definitive proof against vitalism. Some argued that perhaps ammonium cyanate already contained the vital force somehow. But over subsequent decades, chemists synthesized more and more organic compounds from inorganic precursors. By mid-century, vitalism had been largely abandoned. Organic compounds weren't fundamentally different from inorganic ones. They followed the same chemical laws. What made them special was the element carbon. Carbon has a remarkable property. Its atoms can bond with other carbon atoms to form chains, rings, and branching structures of almost unlimited variety and complexity. A single carbon atom can form bonds with up to 4 other atoms. Carbon atoms can form single, double, or triple bonds with each other, creating an incredible diversity of molecular skeletons. On these carbon frameworks, other atoms, particularly hydrogen, oxygen, nitrogen, sulfur, and phosphorus, attach in various arrangements. The result is millions of possible organic compounds, from simple methane with just 1 carbon and 4 hydrogens to complex proteins and DNA molecules with thousands of atoms. 19th century organic chemists worked to isolate, identify, and synthesize these compounds. They extracted substances from plants, animals, and minerals, then used chemical reactions to transform them, break them down, build them up, trying to understand their structures and properties. This work was painstaking. Without modern instruments, chemists had to rely on careful experimentation, noting melting points, boiling points, solubility, and how compounds reacted with various reagents. One triumph of 19th century organic synthesis was the creation of dyes. For millennia, the only dyes available came from natural sources: plants, insects, shellfish. they were expensive and sometimes difficult to obtain. In 1856, an 18-year-old British student named William Henry Perkin, while trying to synthesize quinine, a malaria drug, accidentally created a purple-colored substance instead. He realized this substance could dye silk a beautiful mauve color that didn't fade easily. Perkin's mauve became the first synthetic aniline dye, launching a chemical industry. Within decades, chemists had synthesized dyes in every color imaginable: brilliant blues, deep reds, vivid yellows, rich greens. These synthetic dyes were cheaper and often more vibrant than natural dyes. They transformed fashion and textile industries. The dye industry also drove advances in organic chemistry more broadly. To make dyes, you needed to understand how organic molecules could be modified and assembled. This knowledge proved applicable to other fields, particularly pharmaceuticals. In 1897, chemists at the Bayer Company in Germany synthesized a modified form of salicylic acid, a compound found in willow bark that had pain-relieving properties but caused stomach upset. The modified compound, acetyl salicylic acid, was less irritating but just as effective. Bayer marketed it as aspirin, and it became one of the most successful drugs ever developed. Aspirin was the first of many synthetic pharmaceuticals that would follow. By understanding the chemistry of organic compounds, scientists could design molecules with specific desired properties: drugs to fight disease, anesthetics to eliminate pain, antibiotics to kill bacteria. The early 20th century saw the rise of polymer chemistry, the study of very large molecules made from repeating units of smaller molecules. Natural polymers like cellulose, proteins, and rubber had been known for ages. But chemists began to synthesize artificial polymers with properties that could be tailored for specific uses. In the 1930s, Wallace Carruthers and his team at DuPont created nylon, a synthetic polymer that could be drawn into strong, flexible fibers. Nylon stockings, nylon parachutes, nylon rope. The material had countless applications and demonstrated that chemists could create entirely new substances with useful properties. Plastics, synthetic rubbers, synthetic fabrics, all emerged from organic chemistry laboratories in the early to mid-20th century. These materials transformed daily life. They were cheap to produce, easy to mold into various shapes, and often more durable than natural materials. The 20th century became, in many ways, the age of synthetic materials, and organic chemistry was at its heart. Organic chemistry also illuminated the chemistry of life itself. Biochemists studied the organic compounds that made up living organisms: proteins, carbohydrates, lipids, nucleic acids. They discovered how enzymes, protein catalysts, controlled the chemical reactions in cells, speeding up reactions that would otherwise take millennia to occur. They unraveled the chemical pathways by which organisms extracted energy from food, built up complex molecules, and broke down waste products. Life was chemistry, fantastically complex and exquisitely regulated, but chemistry nonetheless. One of the greatest achievements of 20th century organic chemistry was the elucidation of DNA's structure. Scientists had known that hereditary information was carried in molecules of deoxyribonucleic acid, but the exact structure of these molecules wasn't clear. In 1953, James Watson and Francis Crick, building on X-ray crystallography data collected by Rosalind Franklin and Maurice Wilkins, proposed that DNA had a double helix structure. Two strands wound around each other like a twisted ladder. The sides of the ladder were alternating sugar and phosphate groups, and the rungs were pairs of nitrogen-containing bases. Adenine paired with thymine, guanine paired with cytosine. This structure immediately suggested how heredity worked. If the two strands separated, each could serve as a template for building a new complementary strand. The sequence of bases along the DNA strand was a code, storing information that could be copied and passed to offspring. Understanding DNA's chemistry opened the door to molecular biology, genetic engineering, and eventually the ability to read and edit the genetic code itself. Organic chemistry thus connected the chemistry of molecules to the chemistry of life, the chemistry of materials to the chemistry of medicine. It showed that carbon's ability to form complex structures made possible the diversity of substances in the world, from the simplest methane molecule drifting in space to the elaborate proteins folding in our cells. 20th Century Revolution. The 20th century brought revolutionary changes to chemistry, driven partly by new instruments and techniques, but more fundamentally by new theories about matter's deepest nature. The discovery of atomic structure and the development of quantum mechanics transformed chemistry from an empirical science of observation and experimentation into one that could, at least in principle, be derived from fundamental physical laws. The key insight was that chemistry was ultimately about electrons. When atoms form bonds, they don't merge their nuclei. The nuclei stay distinct. What happens is that electrons, the negatively charged particles orbiting the nucleus, are shared or transferred between atoms. In a covalent bond, atoms share pairs of electrons, each atom contributing electrons that then orbit both nuclei. In an ionic bond, one atom gives up electrons to another, creating charged ions that attract each other. All chemical reactions involve rearrangements of electrons. But electrons don't behave like tiny billiard balls orbiting the nucleus like planets around a sun. Quantum mechanics, developed in the 1920s, revealed that electrons existed in states described by wave functions, probability distributions that told you where you might find an electron if you looked for it. These wave functions had specific allowed shapes and energies, determined by solving Schrödinger's equation, a fundamental equation of quantum mechanics. In 1927, Walter Heitler and Fritz London applied quantum mechanics to the simplest possible molecule, hydrogen. Two hydrogen atoms bonded together. They showed that when two hydrogen atoms approached each other, their electron wave functions overlapped, and this overlapping lowered the energy of the system. The atoms attracted each other, forming a stable bond. For the first time, a chemical bond had been explained from first principles of physics. This was the birth of quantum chemistry. Linus Pauling, an American chemist, became one of the pioneers in using quantum mechanics to understand chemical bonds. In the 1930s, he developed concepts like orbital hybridization, which explained why carbon atoms formed 4 equivalent bonds in a tetrahedral arrangement, and electronegativity, a measure of how strongly atoms attracted electrons in a bond. Pauling's book, The Nature of the Chemical Bond, published in 1939, became one of the most influential chemistry texts of the century. It showed how quantum mechanics could be applied to understand molecular structure and reactivity. Not all chemical bonds could be easily calculated using quantum mechanics. The equations became impossibly complex for molecules with more than a few atoms. But even without exact calculations, quantum mechanics provided conceptual frameworks that explained why atoms bonded in certain ways, why some molecules were stable and others weren't, why reactions proceeded along certain pathways. Chemistry became theoretically grounded in a way it never had been before. Instrumentation also advanced dramatically. X-ray crystallography, developed in the early 20th century, allowed chemists to determine the precise three-dimensional arrangement of atoms in crystals. By directing X-rays at a crystal and analyzing the pattern of diffracted rays, scientists could work backward to calculate where atoms must be positioned. This technique revealed the structures of everything from simple salts to complex proteins, including the double helix of DNA. Spectroscopy became an essential tool. Different molecules absorbed and emitted light at characteristic wavelengths, creating unique spectral fingerprints. Infrared spectroscopy revealed which functional groups were present in a molecule. Nuclear magnetic resonance spectroscopy, developed mid-century, provided detailed information about molecular structure by detecting how atomic nuclei behaved in magnetic fields. Mass spectrometry measured the masses of molecules and their fragments, helping identify unknown compounds. These instruments transformed chemistry from a science of laborious wet chemical analysis to one where structures could be determined quickly and accurately. Nuclear chemistry emerged as a distinct field. Following the discovery of radioactivity and the development of nuclear physics, chemists learned to work with atomic nuclei, inducing nuclear reactions and creating new isotopes and elements. The Manhattan Project during World War II brought together physicists and chemists to produce enriched uranium and synthesize plutonium for atomic bombs. After the war, nuclear chemistry continued as scientists created elements beyond uranium, extending the periodic table into regions that didn't exist naturally on Earth. These transuranium elements were incredibly unstable, lasting sometimes only fractions of a second before decaying. But their synthesis showed that the periodic table's pattern continued, that there was no upper limit to how many protons you could pack into a nucleus, at least in principle. Biochemistry exploded as a field in the 20th century. The structure of proteins was worked out, showing how chains of amino acids folded into precise three-dimensional shapes that determined their function as enzymes, antibodies, or structural components. The pathways of metabolism were mapped, showing how organisms broke down nutrients and built up complex molecules. The genetic code was cracked, revealing how sequences of 3 DNA bases specified which amino acids should be assembled into proteins. This knowledge made possible genetic engineering, the deliberate modification of organisms by altering their DNA. By the late 20th century, scientists could insert genes from one species into another, creating bacteria that produced human insulin, plants resistant to pests, even animals that glowed with jellyfish proteins. The development of computational chemistry, driven by increasingly powerful computers, allowed chemists to simulate molecular behavior, predict reaction outcomes, and even design new molecules with desired properties before ever synthesizing them in a lab. Quantum chemical calculations that would have taken centuries by hand could be completed in seconds. This opened new frontiers in drug design, materials science, and understanding reaction mechanisms. Environmental chemistry also became crucial. As the chemical industry grew through the 20th century, so did awareness of its environmental impact. Synthetic pesticides like DDT, once hailed as miraculous, were found to accumulate in food chains and harm wildlife. Chlorofluorocarbons, used as refrigerants and aerosol propellants, were discovered to be destroying the ozone layer that protected Earth from ultraviolet radiation. Understanding these problems required sophisticated chemistry, tracing how molecules moved through the environment, how they were transformed by sunlight and microorganisms, how they affected living systems. Solutions also required chemistry, developing alternative compounds that were effective but less harmful, designing processes that minimized waste and pollution. By the end of the 20th century, chemistry had become an incredibly diverse and powerful science, with subdisciplines devoted to every aspect of matter and its transformations. But certain principles remained constant. Chemistry was about understanding matter at the molecular level, about predicting how substances would behave, about designing and creating new materials with useful properties. From ancient fire to quantum calculations, from alchemical dreams to engineered proteins, the thread remained unbroken. Modern chemistry and beyond. As we move deeper into the 21st century, chemistry continues to evolve and expand its reach. New frontiers have opened, new tools have been developed, and new connections have been forged with other sciences. Modern chemistry is increasingly interdisciplinary, collaborating with physics, biology, engineering, and materials science to address some of humanity's most pressing challenges. One major area of focus is green chemistry, also called sustainable chemistry. This movement aims to design chemical products and processes that minimize or eliminate hazardous substances, reduce waste, and use resources efficiently. Traditional chemical manufacturing often generated large amounts of toxic byproducts and required harsh conditions. Green chemistry principles encourage using renewable feedstocks, designing degradable products, using catalysts to increase efficiency, and thinking about the entire life cycle of a chemical product from synthesis to disposal. The goal is to make chemistry not just effective, but sustainable, ensuring that our chemical industries can continue without degrading the environment. Nanotechnology has become another crucial frontier. At the nanoscale, roughly 1 to 100 nanometers, materials often have properties quite different from their bulk properties. Gold nanoparticles can appear red or purple rather than golden. Carbon arranged as nanotubes can be incredibly strong yet lightweight. By controlling matter at this tiny scale, chemists can create materials with tailored properties, ultra-strong composites, precise drug delivery systems, catalysts with enormous surface areas, electronic components just a few atoms wide. Materials science, always closely tied to chemistry, has seen remarkable advances. Scientists have created metamaterials with properties not found in nature, such as negative refractive indices that could enable cloaking devices. Self-healing materials that can repair damage automatically have been developed. Researchers are working on programmable matter that can change its shape and properties on command. These aren't science fiction, they're cutting-edge chemistry and materials, science pushing the boundaries of what's possible. In pharmaceuticals, modern chemistry has enabled precision medicine, where drugs are designed for specific genetic profiles, or even individual patients. Cancer treatments increasingly target specific molecules found only in cancer cells, sparing healthy tissue. Antibody-drug conjugates combine the targeting ability of antibodies with the killing power of toxic drugs, delivering poison directly to diseased cells. Chemical biology has emerged as a field using chemistry to probe and manipulate biological systems, creating new tools for understanding life and treating disease. Energy storage and conversion have become critical areas of chemical research. As the world transitions away from fossil fuels, we need better batteries for electric vehicles and grid storage, more efficient solar cells, improved fuel cells, and new ways to store energy from intermittent renewable sources. Chemistry is central to all these technologies. Better batteries require understanding ion movement in electrolytes, electron transfer at electrodes, and preventing degradation over thousands of charge cycles. Each improvement comes from chemical insights and innovations. Catalysis, the use of substances to speed up reactions without being consumed themselves, remains one of chemistry's most important areas. Catalysts make possible reactions that would otherwise be impossibly slow or require extreme conditions. The Nobel Prize in Chemistry in 2021 was awarded for developments in asymmetric organocatalysis, methods for using small organic molecules as catalysts to construct specific mirror image versions of molecules, crucial for pharmaceuticals, where the wrong mirror image can be ineffective or even harmful. Every advance in catalysis makes chemistry more efficient and sustainable. Artificial intelligence and machine learning are increasingly being applied to chemistry. AI can predict how molecules will react, suggest synthetic routes to complex compounds, analyze spectroscopic data, and even propose entirely new molecules with desired properties. Machine learning algorithms trained on vast chemical databases can find patterns that human chemists might miss. This isn't replacing human creativity and insight, but it's becoming a powerful tool that enhances what chemists can do. Chemical education has also evolved. Modern chemistry students learn not just to memorize reactions and formulas, but to think about mechanisms, to understand why reactions happen the way they do, to connect chemical behavior to molecular structure. They learn to use sophisticated instruments, to work with large data sets, to think about the ethical and environmental implications of their work. Chemistry education prepares students not just to work in labs, but to address global challenges that have chemical dimensions. Climate change, water purification, food security, disease treatment. Looking forward, chemistry faces exciting challenges. Can we develop truly efficient artificial photosynthesis to capture carbon dioxide and produce fuels, mimicking what plants do? Can we create new antibiotics to combat drug-resistant bacteria? Can we design materials that make fusion power practical? Can we develop chemical processes to recycle plastics efficiently, closing the loop on material use? Can we understand the chemical origins of life itself? How simple molecules became self-replicating systems? These questions don't have easy answers, but chemistry has repeatedly shown its power to transform the apparently impossible into the routine. The same science that turned alchemy's dreams into chemical reality, that built our understanding from Democritus's atomos to quantum chemistry, continues to grow and adapt. Chemistry remains what it has always been: humanity's way of understanding and transforming matter, of taking the world as it is and imagining what it might become. Conclusion. And so we've journeyed through the long story of chemistry, from ancient fires flickering in the darkness to electron orbitals described by quantum equations, from alchemists in their laboratories seeking to transmute lead into gold, to modern chemists designing molecules atom by atom. It's a story of human curiosity and persistence, of gradual understanding built on countless experiments, both successful and failed. Chemistry isn't just a collection of facts and formulas. It's a way of seeing the world. When you understand chemistry, even a little, you begin to see the invisible transformations happening everywhere around you. The rust forming on iron, the bread rising with yeast, the battery powering your phone, the medicines fighting disease in your body, the photosynthesis in leaves capturing sunlight. All of it is chemistry. Atoms rearranging themselves according to consistent principles that we've slowly, patiently learned to understand. The story of chemistry is also deeply human. It's filled with brilliant insights and stubborn mistakes, with collaboration and competition, with the slow accumulation of knowledge across generations. Every element in the periodic table represents someone's discovery. Every chemical principle bears someone's name because they were the first to recognize and describe it. Behind the equations and structures are people who devoted their lives to understanding matter's secrets. As you drift towards sleep tonight, surrounded by the chemical world, remember that you are chemistry too. The atoms in your body were forged in stars that died billions of years ago. The molecules that make you up are constantly being rearranged, broken down and rebuilt, in reactions so complex and so precisely controlled that we are still working to understand them all. You are a chemical system of extraordinary complexity and elegant design, a temporary arrangement of matter that can somehow contemplate its own existence. If you found tonight's journey through chemistry's history peaceful and enlightening, if it helped you wind down or sparked your curiosity, please consider liking this video and subscribing to the channel. It helps other seekers find their way here, one quiet exploration at a time. Sleep well, rest deeply, and dream of the invisible world of atoms and molecules dancing their eternal dance. Good night.